For most of human history, our story was written in fire. We gathered around its warmth, used its light, and learned to control its power. But fire, as vital as it was, is only a hint of the energy hidden within matter itself. Imagine looking up at the night sky. Stars, the moon, all seemingly serene. For millennia, we thought that was the whole story. Then we built telescopes and microscopes, discovering a universe in a drop of water. Atoms, the building blocks of everything. If you enjoyed the video, please like and subscribe. This was a turning point, the realization that the greatest mysteries were not just in the cosmos, but inside everything around us. The atom's world is strange, a dense nucleus orbited by electrons, governed by invisible forces. For a long time we thought atoms were unchanging, the fundamental bricks of reality. But some atoms are unstable, holding a hidden internal fire far more potent than any flame. Unlocking this secret required a new way of thinking, embracing the bizarre quantum world. Our journey took us from the comfort of a campfire to the heart of matter itself. We learned that the same forces making stars shine could be brought down to Earth. This wasn't magic, it was science, driven by relentless curiosity. We pushed to understand the fabric of the cosmos and our place within it. The atomic age was dawning, and humanity was ready to explore. The story of energy was about to be rewritten, and it all began with a spark. The ancient alchemists dreamed of turning lead into gold, but the real transformation happens in the heart of the atom, radioactivity. Imagine an atom's nucleus as a castle. Some are stable, others, like uranium, are built on shaky ground. These unstable atoms spontaneously shed parts of themselves, releasing bursts of energy and transforming into new elements. This is nature's alchemy, happening all around us, all the time. A uranium atom might become thorium, not by magic, but by the laws of physics. Each radioactive element has a unique half-life, a cosmic clock ticking away, reminding us that even solid matter is in flux. Radioactivity is the universe's way of finding balance, releasing invisible particles and waves as atoms seek stability. For most of history, we were unaware of this cosmic alchemy, but once we detected it, we followed its trail to a new understanding of matter. This discovery led us to a power source, unlike any we'd ever known. The secret of the atom was out, and humanity was ready to harness it. The age of nuclear energy had begun. Once we learned atoms could release energy, we asked, could we trigger this on command? The answer? Nuclear fission, splitting the atom's nucleus. Picture a large, unstable uranium nucleus. Hit it with a neutron and it splits, releasing energy and more neutrons. These neutrons strike other nuclei, creating a chain reaction, a cosmic domino effect. It's like a room full of mousetraps. One sets off two, which set off more, and so on. In a nuclear reactor, we control this chain reaction with rods that absorb extra neutrons, keeping the process steady. This controlled splitting releases tremendous heat used to boil water, create steam, and turn turbines for electricity. It's a delicate dance, splitting atoms to power cities. Fission unlocked a new era of energy. But it also brought new challenges and responsibilities. The power of the atom was now in our hands, and the world would never be the same. The chain reaction had begun. If fission splits atoms, fusion brings them together, the process that powers the stars. In the sun's core, hydrogen atoms fuse under immense heat and pressure, forming helium and releasing vast energy. To make fusion happen, you must overcome the natural repulsion between atomic nuclei, requiring temperatures hotter than the sun. When fusion occurs, a tiny bit of mass vanishes, transformed into pure energy. Einstein's ELMC2 in action. This is the light that warms our planet. On Earth, scientists are racing to replicate fusion, aiming for clean, limitless energy. The fuel is hydrogen, abundant in water. The byproduct is harmless helium. No long-lived radioactive waste, no risk of meltdown. Mastering fusion would be like capturing a piece of the sun. It's one of humanity's greatest scientific quests. The dream, safe, sustainable energy for all. The challenge, making a star on Earth. We have two ways to unlock atomic power fission. Splitting heavy atoms and fusion joining light ones. Fission is proven, powering cities for decades. A tiny uranium pellet can match a ton of coal with no greenhouse gases. But fission creates radioactive waste and carries safety concerns. Fusion, the dream of tomorrow, uses hydrogen from water and produces only helium. It's safer. If containment fails, the reaction stops. But achieving fusion's extreme conditions is a monumental challenge. Fission is today's reality. Fusion is tomorrow's promise. One splits the universe's heaviest elements, the other mimics the stars. As we seek clean energy, we weigh the practical power of fission against the perfect promise of fusion. Both paths lead us beyond the fires of our past. The future depends on the choices we make. From taming fire to building artificial suns, our journey is driven by curiosity. We've peered into atoms and found a power greater than our ancestors imagined. This wasn't just about energy, it changed our view of reality. We learned matter and energy are two sides of the same coin. Splitting the atom gave us power and responsibility. The same process that lights cities can also destroy them. The future depends on our wisdom as much as our knowledge. Will we use atomic power for a sustainable world or fall victim to our own cleverness? The science is here. The choice is ours. Our journey continues toward a brighter destiny among the stars.